Welcome back to my maths channel. It's time for more study on mathematics. Today, Mr. John will go through with you an interesting but tricky geometry question from the 2020 Australian Mathematics Competition. The reason I chose this question is because it covers many important and commonly used geometry concepts. Solving this question is not easy because it involves many logical steps. Hopefully, by the end of the video, you'll be able to understand how to better approach a rather difficult mathematics question, how to apply various math theorems correctly, and of course, do well in your exams. Now, before we get started, I'd like to talk about the required knowledge of this question. Firstly, basic plane geometry concepts. There are parallel lines, right-angled triangles, isosceles triangles, and similar triangles. In particular, how to prove two triangles are similar using pairs of angles with the same measure. Secondly, circle geometry theorems such as inscribed right-angle theorems and tangent lines to a circle. Now, if you don't understand the theorems fully, that's okay. I'm going to explain them briefly and show you how to use them in this question. And of course, if you like, I'm more than happy to do more videos to explain the theorems in greater detail. Hence, let's get started. The first step is to visualize this question. As you can see, here I have drawn a perfectly rounded circle centered at point O, and it inscribes a right-angled triangle with the right angle at angle ACB, and also drawn two parallel lines AF and CD, with line CD also being the tangent line to the circle at point C. As you can see, what we need to prove is that AB is perpendicular to CF. Hence, I also label the intersection point between AB and CF as point G. Here, I have written down all the information I found from the question by analyzing each sentence and translating them from English to mathematics. See how I have simplified the entire question into just 5 dot points. This is because in a way, math is a beautiful and concise language by itself. The first dot point says angle ACB is 90 degrees, followed by line CD is actually a tangent line to the circle at point C. Then CE equals to ED and line AF is parallel to CD. The last dot point is the question we need to solve, which is AB perpendicular to CF. How do we solve it? Actually, like many other math questions, there are multiple solutions. The most intuitive way I found is by proving that angle CGD is 90 degrees. However, if you can find an easier method or simply just an alternative approach, please do post your solutions down in the comment section below. Okay, let's now get started. The first theorem we need to apply is the inscribed right triangle theorem, which says when a right-angled triangle is inscribed by a circle, then its hypotenuse becomes the diameter of the circle, and triangle ABC is just such a right-angled triangle inscribed by the circle centered at point O. Therefore, AB is the diameter of the circle, which makes AO equals to BO equals to CO because the radii of the circle. Next, line CD is a tangent line to a circle at point C, therefore CD is perpendicular to CO and angle OCD equals to 90 degrees. Now, it is easy to observe that the right angle ACB is made up of two angles, angle ACO and angle OCB. The other right angle OCD equals to angle OCB plus angle BCD. Now, by cancelling out the two OCBs on both sides of the equation, we get that angle ACO equals to BCD, and we can label this as alpha. Furthermore, because AO equals to CO, hence triangle ACO is isosceles, which makes angle CAO equals to angle ACO also equals to alpha. Now, let's look at the two parallel lines. AH is parallel to CD, and because CH is a line cutting through both parallel lines, therefore, by the alternate angle theorem, angle BCD equals to angle CHA also equals to alpha. And let's label all the alpha on the graph to better visualize the situation. Now, we have almost exhausted all information given by the question. The only info we have not used is that point E is a midpoint of CD. Now we're going to use it and show that actually point F is also midpoint of AH. You can probably already guess that by looking at the graph. However, as mathematicians, we want to prove it in rigorous approach, and we're going to prove by using similar triangles. The first pair of similar triangles we're going to examine is triangle CBD and triangle HBA. It is pretty simple to show that they're similar triangles because angle BCD equals to angle BHA equals to alpha, angle CBD equals to angle HBA as their vertical angles. Therefore, the two triangles are similar. Now, recall the properties of similar triangles. All their corresponding sides actually in the same proportion. This means that BC over BH equals to BD over AB equals to CD over AH, which gives us equation 1. The next pair of similar triangles we're going to examine is triangle CBE and triangle HBF. Similarly, angle BCE equals to angle BHF equals to alpha, angle CBE equals to angle HBF as their vertical angles, hence they're similar triangles. Therefore, we see that CE over HF equals to BE over BF equals to BC over BH, which gives us equation 2. Now, looking at the two equations, we see that BC over BH actually appears twice. This means that we can equate the two equations and show that actually CD over AH equals to BC over BH equals to CE over HF, which is equation 3. Now finally, we can apply the information that CE equals to ED equals to half of CD, and we substitute this into equation 3. And by cancelling out the two CDs on both sides of the equation, we get the important result that HF over AH is a half, which then means HF equals to AF equals to half of AH, and hence F is a midpoint of AH. This leads us to the final section of the solution. Observe that triangle ACH is a right-angled triangle, and using our previously proved result that F is the midpoint of its hypotenuse AH, we can actually apply the reverse of the inscript right triangle theorem and show that there must be a circle that inscripts triangle ACH, and it is centered at point F. This means that not only AF equals to FH, but also equal to FC, because they're all radii of the circle. This means that angle FCH must equal to angle CHF equals to alpha. Hence, we know that angle GCD equals to angle GCB, which is the same as angle FCH plus angle BCD equals to 2 alpha, and we can label this as equation 4. Now, let's look at triangle AOC and line AD. Because the sum of all angles in a triangle is 180 degrees, and the two angles on a straight line also add up to 180 degrees. Therefore, this means that angle ACO plus angle CAO plus angle AOC equals to 180 degrees, and angle AOC plus angle COB also equals to 180 degrees. Now, by cancelling out the two AOCs on both sides of the equation, we arrive at a pretty important result that angle COD actually equals to 2 alpha. And we can label this as equation 5. Why do we do this? This is because by looking at equation 4 and equation 5, angle GCD must equal to angle COD, and we can use this to prove that triangle COD is actually similar to triangle GCD, because we have two pairs of angles with the same measure, that is, angle GCD equals to angle COD equals to 2 alpha, and the angle D is shared by the two triangles. Hence, we're able to show that angle CGD must equal to angle OCD equals to 90 degrees. And finally, this gives us the solution that AB has to be perpendicular to CF, and we're done. Thanks for following. I hope you now understood how to prove this tricky geometry question, and you have learned something useful from me. Thank you very much, and see you next time. Bye.